We're going to talk a little bit about the general idea behind half-life, and then just a couple of quick definitions about fission and fusion. It won't be nearly as complicated as what we had in the last lesson, and it doesn't, you'll see some questions on it, but it's, again, very little math. It's not going to be quite as difficult. So let's get going. First off, what half-life is half-life is how long it takes for half of a radioactive sample to decay. We talked about what radioactivity was in the last vodcast, that basically that when we talk about radiation or radioactivity, it means that there's an unstable nucleus and it's trying to make itself more stable by getting rid of something, okay, an alpha particle, a beta particle, some energy, whatever that is, okay? So half-life is how long it takes a given sample to decay to basically half of itself. And it's kind of hard for you guys to see this chart. And let me see if I can blow this up just a little bit. But this is a chart from one of the textbooks that essentially just talks about what are some half-life values for certain isotopes. So just if you look at just a couple of these, let me see if I can click the highlighter on real quick. If you look at just a couple of these, so this is a tritium, okay, hydrogen. We're going to come back to that a little bit later. Got a half-life of 12.26 years. So what that means is if we had, say, a 100-gram sample, that in 12.26 years, that 100-gram sample would turn into a 50-gram sample. Okay, and so we see a lot of different half-lives here for a lot of different isotopes. This is by no means an exhaustive or a really long list. This is just a few sort of common ones. You see that some of these have an incredibly long one. So 48 billion years. Obviously, we haven't even had 48 billion years of time yet. So that's obviously an estimate. A real big one for us down here is U-238. Has a half-life of 4.51 billion years. Okay, so some of these have really long half-lives. Some of them have really short ones. If you look up here at Krypton, Krypton 93 has a half-life of 1.3 seconds. So not terribly long at all. So it all depends on what the isotope is. They all have their individual half-lives. And so what that means is, again, if we start with 100 grams of something, then after one half-life, okay, it would change into 50 grams, okay? So that would be one half-life. Or we could use the symbol for half-life, which is something like that. Again, my drawing is awesome. So if we had another half-life after that, that would be 25 grams would be left, okay? And after another half-life, 12.5, that's 12.5, and so on and so forth. And so that's one half-life, two half-life, three half-lives. And that's what we can sort of see on this graph up here. If we look at this, the first half-life is right here, okay? And we could tell how much is left at that point. We can read back along the graph, and we got 50 left. At two half-lives, okay, right here, we've got 25 left, and then at 3, we've got 12.5, and if we went on to 4, we would have 6.25, okay? It basically splits in half every time. Now, what that means is, of course, you're always going to have a little bit. It might be a really small amount, but you never get to 0, really, because you're just splitting it in 2 every time. If you take some higher math classes later, we'll call that limit theory. So, a big question that pops up for us then is how then are we able to find half-life? And there's some mathematical ways to do it, but we're really not going to get into that, which you're probably pretty thankful for. Instead, what we're going to worry about is looking at a graph and being able to find half-life that way. Okay? So this is a half-life graph of a radioactive element. And if you look, what we have here on the side is how much of it we have, amount in grams. And down here on the bottom, we have time in days. So this is obviously something with a pretty short half-life. And so the way that we would then find out how much we have is that we would look at our graph, and we're going to start out with 50. And so if I want to see half-life, half-life then is going to be at about 25. Half of 50 is 25. And so that's this point right here on the graph. Okay? So that is basically after one half-life has gone by. So if I want to see how long that half-life is, then I would basically take a line and from that point on the graph, draw it straight down, or as straight as I can, and where that intersects with the graph, that is what the half-life is, because that's how long it took for one 50-gram sample to decay to half of itself. And it looks like that is about 25 days. Maybe a little bit less, maybe like 24 or something. And you could check that by going to the next half-life. Okay, so right here, that's at about 12.5. Okay, that's half of 25. And if we drew our line straight down here, it looks like it's, to me, a little less than 50, so maybe it's like, 49 days or something, and that would be 49 days, or that would be added to this amount. So basically 24 or so here, 24 or so here, and it looks like that's pretty consistent. Each time it's a little under the big bar, so we're probably at about a 24-day half-life. Okay? Now again, how do we make sure that we've got a pretty good handle on this? This is a real element, a real isotope. It tells you what it is up here. This is carbon-14, very common. This is what we use for radiocarbon dating. Okay, so we're going to look at what we start with, which is up here, 100 grams. And so we're going to go down to 50 grams right here. We'll draw a line across till we get to the graph, the line on the graph. So we hit it right there. And then we're going to draw a line straight down from there, straight as I can make it anyway. And so then we're going to figure out where is that at? I mean, like, what is that value? So 10,000 is here. And we've got 5 boxes, 1, 2, 3, 4, 5. So that means that each box is 2,000 years. So that means 2,000, 4,000, 6,000. So a little under 6,000. Let's say maybe, and obviously we're gonna be kind of we're gonna be making an estimate here when we do that. But I would say probably about 5,700 to 5,800. Okay. And really, we could kind of go back and check that because, remember, we got that table of half-lives at the beginning. And so if we go back and see if we can find carbon-14, which is right here, okay, C14, it is 5,730 years. So a pretty good estimate. That was about what the half-life is. And we just found that by using the graph. And again, there's some mathematical ways to do it, but we don't have to make it all that terribly complicated. Okay, so that's how we find half-life on a graph, and we'll have a couple of examples of that coming up for you to practice as well. So let's move on to the next couple of things. Fission and fusion are the things that we want to talk about, and it's basically important to know the difference between these two ideas, and they're not terribly complicated. What fission means, okay, so when you see the word fission, okay, pronounced sort of like if you had an accent on fishing, okay, fission. What fission is the splitting, okay, sorry for the writing there, of a nucleus, okay, or sometimes you'll just hear it referred to as the splitting of an atom. Fission means splitting. To be honest, it meant the same thing in biology. If you remember biology class, you probably talked about binary fission, and that's where a cell split into 2 separate cells, so fission means the same thing there. Okay, so it's the exact same thing, nothing terribly new there. Fission is splitting, okay? And we'll see in a minute here that that's different than fusion. So what's going on in fission is this, okay? We have a neutron, and we're going to basically fire a neutron at an unstable nucleus, okay? This is a U-235 atom, which means it's uranium-235. This is what they spent all the effort. This is why Oak Ridge is what it is today, is that they were trying to pull out the U-235 out of uranium samples because it's more fissionable. It splits apart better. So when they were trying to develop nuclear weapons, this is what they did at Oak Ridge. That's the whole, oh my gosh, this is going to be bad. This is the whole reason that they did this. They did this at the, you guys have probably heard these names, at the Y12 and the K25 plants. This is part of what they did, was they tried to enrich this. If I'm correct, I think K25 is actually where they started it at. So I'm sure someone can correct my history on that. But that's what they did, is they were trying to enrich it to get this isotope. So why did they need that isotope so bad? Because if you fire a neutron at it, it splits into 2 pieces, okay? And this right here, this is an energy measurement, okay? That says 200 mega electron volts. That basically is a lot of energy, especially for one atom. So splitting one atom of this breaks into two different atoms, okay, into a barium atom and a krypton atom. And it also gives off 2 neutrons. Now this is what's important, because you put 1 neutron in, and then 2 neutrons and a bunch of energy are going to come out. So what's important about those 2 neutrons is that leads us to this, okay? This big giant reaction is what we call a chain reaction. This is that initial thing that we looked at on the last slide, okay? So we're firing a neutron, hits the uranium splits up into its 2 atoms, but more importantly, it produces more neutrons. So those two neutrons go in and split another atom. And then those two go on and split another atom. Okay, and then they split another atom. So what a chain reaction is a reaction where each split generates enough neutrons to keep the reaction going. Okay, and it just goes on and on by itself. And that's essentially what leads to a nuclear explosion. Is if it's uncontrolled chain reaction, then eventually all that energy gets released and it's an explosion. There's still chain reactions going on in nuclear reactors. The difference there is that they control it. They have what they call control rods that they stick into the reactor, and they're going to absorb some of these neutrons so that they control how many splits are happening. Okay, so a chain reaction just means that you're going to fire that one neutron in, and you're going to get enough neutrons out to keep the reaction going on its own. It's what we would typically refer to as self-sustaining. Okay, in other words, you don't have to keep putting neutrons in. That it keeps going on its own. And that, obviously, for the case of a nuclear bomb or something, that's kind of what you want. You want it to generate a massive amount of energy and cause that explosion. Okay? So how's that different than fission? Okay? Well, fission, whereas fusion was the splitting of an atom, fusion is essentially the total opposite of that. Fusion is the joining of nuclei. Okay? So you're going to take two nuclei, okay, and you're going to fuse them together. That's where we get the term fusion from, is from fusing things together. They're going to join together. Okay, so in the most common example, and you can do it with other things, but this is the way it normally works, is that we have a deuterium. If you remember, that is one of the isotopes of hydrogen, where it's got a proton and a neutron, and tritium, where we've got a proton and two neutrons, and we're going to force those together. When they force together, they form a helium with a 5 mass, which is unstable. Helium doesn't want to have a mass of 5. Okay, so what it does is it kicks off one of those electrons, and in the process of kicking off that electron, it generates some energy. Okay, quite a bit of energy. And the beauty here is that you're dealing with much smaller masses. So for the same equivalent mass, you're going to get a lot more energy out of fusion than you're going to get out of fission. And if you do fusion the right way, a lot of times the byproducts of it are a lot less radioactive, which is a definite plus. So fusion is joining of nuclei. Fission is splitting of nuclei. Okay? So let's talk real briefly just about a couple of things. Sorry guys, drop my notes. About a couple of things that are common between them that are going to be important for us. So things that make them different and things that make them the same. So what's the same about them? Both, okay, generate a lot of energy. Okay? A lot of energy. And that's what makes both of them useful. That's why we want nuclear power plants, despite the fact that they're at least a little bit dangerous. So on the fission side then, what do we have? We have one atom splitting. Okay? Guys, you'll notice that I got a new pen, but I'm practicing a little bit with the writing of it. Okay? So one atom splitting. Okay? It's fairly easy and controllable. Okay? It's fairly easy to do today. We have nuclear reactors all over the place. Some places like France, they get the vast majority of their electricity from nuclear power. This is what nuclear power plants do basically every day. On the fusion side, so what makes fusion better? Well, first off, let's remember what it is, okay? It's two atoms, okay, forced together, okay? But what makes it really hard is that it takes a lot of energy, okay? A lot of energy or temperature, same thing basically in this sense, a lot of energy or temperature to get it started. In fact, it's about, I think it's something like 25 million Kelvin or 25 million degrees Celsius, I think it is. So you get a lot more energy out, okay? More energy. You get a lot more energy out of fusion, but you have to put a lot of energy in. Okay, so remember those two definitions. Remember how to, we'll get some practice on how to tell what half-life is from the graphs. And that's it for